Hi everybody, welcome back to Calc 3, and today we're going to talk about surface integrals, what I think is probably the most difficult concept in this entire course. Before we define surface integrals, there are going to be two kinds, one for scalar functions and one for vector fields. Before we get to surface integrals for scalar functions, let's revisit line integrals for scalar functions. So if you remember when we talked about line integrals, we wanted to integrate some function over a curve. And the way we did that was we parameterized the curve and we integrated from a to b in the parameter t. We defined the function on the curve by plugging the parameterization into the function, and then we multiplied by the magnitude of r prime, which was our ds element, our arc length element. And then arc length was the same as integrating 1 over the curve ds, which was the magnitude of r prime dt. So now we're not concerned about integrating over curves. We want to integrate over a surface, so we're going up a dimension. And what we consider now is a function of 3 variables. We need to make sure it's a function of 3 variables because our surfaces are going to be outside of just the xy plane. We want this to be continuous, and we want to integrate this over a smooth surface. We defined what smooth surfaces were in the last section. Right, they have a parameterization that's continuous on the parameter domain, on the interior of the parameter domain, and the cross product of the first partial derivatives of that parameterization is never 0, meaning we can always find a normal vector on the interior of the parameter domain. So if our surface is smooth and we have a parameterization given here, then the surface integral of our scalar function is the integral over S, that's our surface, of the function f, d sigma, where d sigma was our surface area element from the last section. So then how do we implement this? It's the double integral over d of our parameterization plugged in to our function times the magnitude of the cross products of the first partial derivatives of our parameterization. So the partial derivative of r with respect to u, cross product with the partial derivative of r with respect to v, take the magnitude of that cross product, dA. And the area of S, the surface area, this is what we did in the last section. You integrate 1 over the surface, and you get the surface area integral that we talked about in the last section. So now just to remind you the difference between S and D, it's similar to the difference up here between C and the interval AB. C is the actual curve we integrated over for our line integral, and the interval A to B was the interval where t took values. So the same thing down here. S is the actual surface that we want to integrate over, and D is the domain where u and v take values, where our parameters take values. So now D is some two-dimensional region. And when we do an example, I'll show you the difference between the two. And let's do an example now. So we want to evaluate this double integral, this surface integral, x plus c, where the surface is a portion of the cylinder y squared plus c squared equals 9 between x equals 0 and x equals 4. Okay, so I'm going to break this down into steps. There's a lot that goes on here. We eventually want to set up an integral that looks like this. But if we break it down, let's start by parameterizing the surface and then finding bounds of integration. So we're going to figure out what u and v are and then find bounds on u and v. So it may help to draw the surface. So let's go ahead. I've drawn the surface here. Here it is. Here's the cylinder, making circles in the yz plane. This is the cylinder y squared plus c squared equals 9. The radius of this circle is 3. And then the cylinder is parallel to the x-axis. So it's a cylinder of radius 3 parallel to the x-axis. So if we want to parameterize this, we can use the shifted cylindrical coordinates that we talked about at the very end of section 16.5, where I said we have cylindrical coordinates, but you can also shift them around so that instead of z being the variable that stays the same, when you switch to cylindrical, x is the variable that stays the same. Because really we want to make circles in y and z. So we let y equal r cosine, z equal r sine. We could also switch these. It would just change the way the surface is traversed, which doesn't matter at this point. But either one's fine. So let's just stick with this. y equals r cosine, z equals r sine, and x is going to stay x. Now, I still have three variables, r, theta, and x. So I need more information to parameterize this surface to get rid of one of those variables. But I know the radius of this cylinder is 3. So if I want to make sure that these points are all on my cylinder, r is going to be 3. So that's going to stay fixed. So then I can just pick the other two variables, x and theta, to be my parameters. And I just picked x to be u and theta to be v. It really doesn't matter at this point. But with this information, the parameterization for this cylinder, the first component is u, one of our parameters. That's going to be our x variable. The second component is 3 cosine v. So v is our theta variable. And the radius is fixed at 3. And the third component is 3 sine v. So this gives us the surface. I need bounds on u and v. Well, I'm given bounds on x from 0 to 4, so those are going to be the exact same bounds on u. U goes from 0 to 4, and since we're going all the way around, we're getting the entire cylinder, or if you look in the projection into the YZ plane, we get the entire circle. V goes from 0 to 2 pi. Now, here's the perfect time to talk about the difference between S and D. In this problem, S is this cylinder. That's the surface we want to integrate over. D is the domain where parameter takes values, so it's these values over here. So if I were to draw D, I couldn't draw D over here. There are no U's and V's here. It's a different space. It's a parameter space. So D would be a rectangle in the UV plane, some other parameter space, because here U is just going from 0 to 4, V is going from 0 to 2 pi, so U and V can take on any values, any combination of values in these intervals. So that gives me a rectangle. So that's the difference. S is the actual cylinder, but once I parameterized it, I'm only going to integrate over this rectangle. Okay, so that's the first step. The next step is to calculate this surface area element, this d sigma. So we're going to do that in several steps. The first step is calculating these partial derivatives. So now that I have this parameterization, I can take the partial derivatives with respect to u and v. The partial derivative with respect to u, I just get 1 and 0, 0, because there are no u's there. The partial derivative with respect to v, I get a 0 here because there are no v's. And then negative 3 sine v, 3 cosine v. So those are my partial derivatives. The next step is to cross these two. And since I'm going to end up taking a magnitude, the way I set up the cross product doesn't matter. So I just set up my cross product. It doesn't matter which way I set it up. And then I compute the cross product. I'm going to get 0, negative 3 cosine v, negative 3 sine v when I cross those two partial derivatives. And you could verify that on your own, make sure that's correct. And then the last part is I'm going to take the magnitude of this cross product. So taking the magnitude, remember you square the components of the vector, add them together, take a square root. So what ends up happening, if I square these, I get 0 plus 9 cosine squared plus 9 sine squared. I can factor a 9 out. Cosine squared plus sine squared is 1. The square root of 9 is 3. So the magnitude of this cross product is just 3. So d sigma is 3 times dA. But dA, we're just integrating with respect to u and v, so that's du dv. Now, let me pause for a second and point out that when we talked about triple integrals in spherical and cylindrical coordinates, and we talked about double integrals in polar coordinates, we had to multiply our function by a Jacobian. In other words, for double integrals, dA became r dr d theta. For triple integrals, right, in cylindrical, dv became r dr d theta dz, and in spherical, it was rho squared sine phi d rho d phi d theta. So we had to multiply by these Jacobians. In this case, you might say, well, we used cylindrical cylinders here. Do I need to multiply by an r? No, you do not. The reason is, that's what we're doing here. This isn't exactly a Jacobian, but it's still some element we get from changing variables. We're changing variables from x, y, z to the two parameters u and v. So this takes care of what we need to multiply our function by. So you don't need to multiply by an additional Jacobian. This takes care of it. That's a mistake students often make. So this step takes care of what you need to multiply your function by. Now, if for some reason after I compute this element, I decide to change variables again, then you would have to change this appropriately. You might have to multiply by a Jacobian. But if I just stick with the u and v, then this is all I need. Okay, moving on. Our next step, now that we've found the surface area element, is to see what our function is on the surface. How do we define this function just on the surface? So we plug the parameterization into our function. Our original function was x plus z. Our parameterization is u, 3 cosine v, 3 sine v. So we just need to plug this parameterization into our function. So that means wherever I see an x, I put u. Wherever I see a y, I put 3 cosine v. Wherever I see a z, I put 3 sine v. Well, I don't have any y's. It's just x plus z. So my function on the surface is u plus 3 cosine v. These are, if you let u go from 0 to 4 and v go from 0 to 2 pi, these give you the values of this function f on that surface. Now, geometrically, what does this look like? Well, now we're talking about something four-dimensional, right? Because I have a three-dimensional surface, and for each point in the surface, I'm assigning a value based on this function. So it would be a four-dimensional geometric object, or you could think of plotting a color map on the surface. So in other words, assign colors to the real numbers, and then whatever value f gives on the surface, so let's say I pick a point on the surface, I plug it into my function, I get a number, I plot that color at that point on the surface. So that's another way you could represent the values of this function on the surface. Anyway, moving on to integration. Our next step is to set up the integral and actually evaluate it. So we know that we're integrating with respect to u and v. V goes from 0 to 2 pi, u goes from 0 to 4. We're integrating our function, which was x plus z, is now u plus 3 sine v. And now I need this d sigma, which was 3 du dv. So this is our integral. This 3 I can just pull all the way out, which I do here. I can't separate this integral because I don't have a function of u times a function of v. I have a function of u plus a function of v. So this is not separable. So I just have to go ahead and integrate. So I integrate with respect to u. I get 1/2 u squared plus 3u sine v. I plug in my bounds. When I plug in 4, I get 1/2 of 16, which is 8. And then 3 times 4, which is 12. And then the sine v, when I plug in 0, both of those terms disappear. Next, I'm going to factor a 4 out, just to make these constants a little smaller. It doesn't matter, you don't have to do that. But if I factor a 4 out, I get a 12 outside, and now I have this integral in v. If I integrate with respect to v, 2 becomes 2v, 3 sine v becomes negative 3 cosine v, and now I plug in my bounds. So when I plug in 2 pi, I get 4 pi minus 3, because cosine 2 pi is 1. And then I plug in 0, I get 0 here, so minus 0, plus 3, because cosine of 0 is 1. And then the 3's cancel out, and my answer is 48 pi. Alright, let's end this video by talking about how we could have used symmetry in this example to just integrate x instead. So if I go back to my picture, let me put it up quickly. Here was the setup. I wanted to integrate the function x plus z over this cylinder. Well, this cylinder is symmetric in z, meaning if I look at this cylinder, it's a mirror image above the xy plane and below the xy plane. That's how it's symmetric with respect to z. This term z is an odd function in z, so you can think I can split this surface integral into two integrals, the surface integral of x plus the surface integral of z. We can still do that. We can split up integrals over addition and then just write this as two integrals. Well, if I have an odd function in z and I'm integrating over a domain that's symmetric with respect to z, it's the same rules that we had for double integrals. So this is just 0. The integral of z over the cylinder is 0. Now, the integral itself is not 0. I have an odd function in x, that's true, but my surface is not symmetric with respect to x. If it was symmetric with respect to x, I would see the same thing on both sides of the yz plane. I would have a mirror image over the yz plane, but I don't. My entire surface lies on the positive side of the yz plane. There's nothing on the negative side of the yz plane. In other words, there's nothing when x equals a negative number. So this surface is not symmetric with respect to x. So I can't say that the answer is 0. And in fact, after we integrated, The answer wasn't 0, so that wouldn't be true. But if you look at what we had, this was my x term, this was my z term. Everything involving this z term ended up canceling out. So if we trace this, we had 3 sine v, that became 3u sine v, 12 sine v, blah, 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 blah. Down when we integrated, we got 3 cosine v, which gave us negative 3 plus 3. It canceled out. So this answer only came from this term u, integrating u. So we could have just integrated x instead. Now, you don't have to pay attention to these things if you don't want to, but if you notice these things, you can use this symmetry to help you and simplify your problem a little bit. If we had just integrated 3u over this domain, it would have solved us dealing with the trig function, even though this was easy and it didn't matter. So just something to keep in mind. In the next video, we'll continue talking about surface integrals of scalar functions.